Hello everyone, my name is Peter Shields and on behalf of AirMet Scientific, I'm pleased to welcome you all to today's webinar. We're very fortunate to have Volker Brands, the Regional Sales Manager from Narda Safety Test Solutions in Germany, joining us today to present part 2 of our 5G webinar series, 5G Extrapolation to Actual Maximum Exposure. The development of 5G technology has seen new challenges arise in the field of safety and radiation monitoring. Today, Volker will go deeper into the physics behind radiation monitoring and examine the ways in which actual maximum exposure values are calculated when it comes to 5G. So over to you, Volker.
Thanks, Peter, and good afternoon to the whole audience. Thanks, Peter, for organizing that seminar. Let's have a look on the last presentation. Probably some of you have already participated the part 1, which we did on July the 9th, and that was more on the intro and basics on 5G. Now I want to more focus on not only measuring the current exposure, but having a possibility to do an extrapolation to the maximum EME. So we just jump to the slides where I stopped. So the last discussion was on measurement of the current exposure with the selective radiation meter SRM 3006. That is what we discussed, and have the current exposure listed in the summation, in the integration of the bands with all the other contributors of exposure like GSM, DECT, 3G, Wi-Fi, and the non-licensed ISM bands, and where we see 5G by having the integration of the signals. Okay, so sorry. Here's now also the picture to the comments I just made. So that is where we started a month ago with the measurement of the current exposure, and also with a 24/7 measurement possibility with the EME area monitoring probes, the broadband probe and the selective probe. And now let us discuss a little bit how to do a measurement or a calculation to the actual maximum exposure. The issue with the transmitted power of 5G new radio base station is that they strongly depend on the current traffic load and the user behavior. Plus we have the beamforming, which we have discussed also a month ago, the beamforming in horizontal and in the elevation direction, the beamforming both for traffic beam and broadcast beam, and that makes it now much more complex compared to 3G and 4G measurements. So in practice, it means that the current exposure measured within a specific observation time could be much lower than the actual maximum exposure, and many regulators enforce extrapolation to maximum load and to compare this result versus the allowed local limits. By this, it can be assured that the exposure will not exceed the limits any time and anywhere. So that was the approach we already had with 3G and 4G. So for 3G and 4G, we already developed not a broadband, not a selective, but a code selective measurement, and this is allowing the calculation to maximum exposure. So in the past with 3G and 4G, we were using signalization blocks, which are independent from the current load of the base station. By these resource elements, or in LTE, it's called resource elements. In 3G, it's called PC pitch. So it's a kind of beacon, a kind of pilot. If we use older terminology. And this was allowing for calculation to actual maximum exposure that was described in many standards, and that was the method used over the last years. Now, one of my colleagues from R&D wrote an article in the Health Physics journal on the assessment of human exposure now for 5G. And this method I quickly want to present to you, and this calculation scheme. And then at the end of my lecture, I want to give you an outlook. What is the latest discussions, and what could be an implementation for the SRM. So as I said, the full description is available under this link, which we'll also distribute with a soft copy of these slides. The extrapolation to actual maximum exposure for mobile networks is already roughly described in the ITU K100, in the IEC 62232, or the respective European norm 504092. And we are proposing here two different methods to extrapolate to actual maximum exposure. One is in the frequency domain, so frequency selective measurement. That is good enough if you are now in the early phase of 5G introduction. So if the signals, if the traffic load is not too high, and you can see in frequency domain and in time domain, so it's a combined method with a scope mode, time domain, oscilloscopic presentation of signals, and frequency selective measurement, so that you see the complete signal in time and frequency domain, the up and down links, because we're talking about TDD, so you need to exclude the uplinks, the user equipment, which could be dominant if there are any smartphones, mobile phones, or modems nearby your measurement position. And of course, we only want to look on the downlinks, on the signal coming from the base station down to the users. So this method is there, but it's getting a little bit dodgy if there's too much of traffic, because then the separation of the signal in frequency and time domain mode, so the respective synchronization signals which you refer to, are not that easy anymore. Therefore, the ultimate method eventually then will be also the second, the demodulation based measurement. Both methods are based on measurement on signalization components, which are the primary synchronization signal and the secondary synchronization signal, the PSS and the SSS. So if you look to the structure of the transmitted frames of the blocks in the 5G downlink signals, we see subcarriers with 4 symbols, and the PSS and SSS with a one symbol length. If we have a look into the spectrum, into a waterfall spectrum, or what's also called the spectrogram, here measured with a brother instrument of SRM, which is called the IDA2, the Interference and Direction Analyzer, which is same hardware but a little bit different firmware compared to the SRM. Then you can see this structure quite clearly. And now the algorithm is looking like that. You measure the synchronization signal frequency selective. That is what is available today. That is also how the labs, for example, of the vendors of Ericsson and Huawei are currently measuring the exposure. So using the measurement in frequency, from that doing an extrapolation to full bandwidth. Typically it's a TDD system, yes, so you need to have the correction for the uplink time slot. You can verify that, as I already explained to you, in the scope mode of SRM, where you see the uplink and time link then separated in time, and you see the difference. Then the point is beamforming in use, yes or no. If there is no beamforming, you already have the final result, and that is quite a straightforward measurement, which is possible today. If there is a beam forming, then there needs to be some correction of power and gain for the difference between the traffic and broadcast beam. We will discuss this again at the end of my session, because here we still have some area where we need to work on, because recently we found out that the praxis is a little bit more complex than the theory. Nevertheless, I will go through the theory, because more or less this theory will be applied. But recently we have seen that there will be probably a move to another part of the broadcast signal, which is more stable and which is probably more easier to be used for calculation to maximum exposure. So that is the way if you have a measurement in frequency and time domain, and if the cells are still early stage, that means we don't have too much of traffic signals. So and you don't have beam forming, then it's quite straightforward and quite easy, and the old recommendation and standards can still be applied. For the calculation to maximum exposure by in systems which are fully operation, we probably need to go again for a demodulation based solution. But here the question is still what signal to be used. The initial proposal of having here, of using the synchronization signal, seems to be a flawed approach. I will discuss that at the end. So extrapolation to actual maximum exposure, frequency selective measurement, we discussed that. This method requires the so-called scope option. That's the time domain analysis with IQ streaming with 20 megahertz real time, which is typically sufficient to find the signal we refer to in LTE, in UMTS, and in 5G. Second proposed method is demodulation measurement. Here we're still discussing, especially with the vendors, as the likes of Ericsson and Huawei, what is a part of the signal what we can refer to, which is the part of the signal which is stable and which has a clear relationship between the maximum of the broadcast beam and the maximum of the traffic beam. Hence, this approval of this method by national and international bodies is still pending. So the advantages of the measurement based on demodulation is it will be again independent of the traffic situation, like we know it from the 3G and 4G options. It can distinguish between different cells, so you have a clear idea of the contribution of different towers, of different antennas, of different segments, of the different operators, of course, but that is, of course, can be allocated by the frequency spectrum, by the licenses in the auctions. It does not react on signals emitted by mobile phones imported in TDD systems, and we're typically talking about TDD systems. So you cancel out the uplink path, the mobile phone contribution, which can be again significant if you forget to switch off your mobile phone. If you do the test for the SRM and it's just very nearby the antennas, then it would have an effect if you go for frequency selective measurements only and not checking in time domain scope mode and not checking with the demodulated signals. The other steps 2 to 4 are equivalent to both or in both methods. So if we take a look in that SS PBCH block, the broadcast control channel, the synchronization channel, then we see it is not anymore allocated like in the center of the signal, like we had that with LTE. So first of all, you need to check, for example, with max hold during period of low traffic, or when the when the 5G station is still in trial mode. Then you see that this block is now at the left border of the frequency spectrum of the 5G signal. Yeah, so it's at the lower edge of spectrum, and first it has to be located, and then you can make the measurement with max hold. So that was in frequency domain. Now let's have a look with the scope mode in time domain. Again, you see the signal here in the red circle. That is the synchronization signal of interest. You can double check for the length and width of the signal. We have two different synchronization methods here, or modes here, with different subcarrier spacing of the subcarriers. And this is important to verify that there is no higher signal than the synchronization signal, and that you also do not have any uplink signals in TDD from the smartphones. If we zoom this a little bit, we see we have the primary synchronization signal, the secondary synchronization signal, and some other broadcast control channel in that signalization downlink block. Yeah? You can verify by the standards the length of that. It's either 285 microsecond in the 15 kilohertz subcarrier spacing configuration, or 142.8 microsecond in the 30 kilohertz configuration of subcarrier spacing. And also the bandwidth, you can double verify that is also then in frequency domain. The bandwidth of the block in frequency domain is almost double than in the 30 kilohertz subcarrier spacing case. So the resolution bandwidth on SRM in the scope mode or level recorder mode, so both are time domain measurements, you set accordingly to 2 megahertz in the 3.6 megahertz bandwidth case, and to 4 megahertz in the 7.2 megahertz range. Yeah, and put it just to the center frequency where you have found the synchronization signal. Video bandwidth to smooth that signal and to get a reasonable average reading is then accordingly, so the video bandwidth to 1.6 kilohertz in the 15 kilohertz subcarrier spacing case, and to 3.2 kilohertz in the 30 kilohertz. That's it. Then you get that test result, and now you need to put this into this following formula. So the exposure, the maximum exposure index, the IE max, is the square root of the, so it's you get from the level to the power, yeah. So the power is the square root of the level of this synchronization, this secondary synchronization signal, divided by the square root of the reference power, which is allowed, for example, the ICN IRP, the ICNIR value at that frequency range. Then you take the number of channels divided by refer it to one channel, multiply it by two further constants. So here it's shown. So you take the measurement results, then you do the extrapolation to the full load versus bandwidth. So you multiply it by the full frequency bandwidth of the 5G band, which could be 20 megahertz, or in the widest case up to 100 megahertz. A correction if it's a TDD system. So the ratio between the uplink and the downlink time slot. And then last but not least, the most complex and most critical point is the correction for power and gain difference between traffic and broadcast gain. And then you end up with the final result. With the last one, we found out that probably this approach is a flawed approach, so that we probably will not do the measurement of the PSS and SS signals, but refer to other signals. I will come to that in the end. What is the latest status of that? So there will be not a change of that formula, because this formula is correct and can be applied, but that we use a different synchronization or a different part in the signal where it's allowed to have a calculation to maximum exposure, or which is supporting that. So again, putting a little bit more light on this formula. So the E reference is the reference level. I already said that. For example, the ICNIRP general public, or the different values in the different countries. So we have, for example, deviations from ICNIRP in countries like India. They only take 10% of the power density, or also in Poland, Switzerland, Italy. They only take fractions of the ICNIRP level to have a safety cushion, and put in these electrical field strength values, or better the square, so the power. The next is the extrapolation to the full bandwidth. So if it's the maximum possible bandwidth for the lower frequency range of 5G, we have 100 megahertz bandwidth with 30 kilohertz subcarrier spacing. So the total is 275 times 12, so 3,300 subcarriers in total. So we need to calculate on that and put in the ratio between the total subcarriers and the subcarrier of the SSS, which occupies 120 subcarriers. So the respective factor in that case is 26. Yeah, so you would put in here, this term would be 26, 26 times 5. Then the extrapolation to the full load versus the bandwidth. So let's have a look again into the oscilloscopic presentation, where you see the uplinks and the downlinks. So signals you see here is the uplinks, and the gaps are the downlinks. So there is no uplink activity. But if there would be an uplink activity, then you just cancel out. You just reduce the signal, and you take out the uplinks, because we are not looking into the SAR values of these mobile phones. That is another technology, another field of measurements. We only want to look into the downlinks coming from the radio systems. And then last but not least, you have the K system, which is easy if there's no beam forming, and there is the signalization and the traffic load beams are same, then it's set to 1. But if we have this beam forming, then the ratio between the broadcast beam power and the traffic beam power needs to put in here as the K, as the system, as the special system value. So if the antenna gain or the power of the signalization beam is different than the antenna gain or the power of the traffic load, then this factor K system needs to be applied. So the extrapolation to maximum exposure is not trivial, because this beam forming factor is not so easy to define, and the vendors needs to define that depending on their system or the system architecture. With the beamforming antenna pattern for signalization, traffic can be totally different. That is also what we found out with recent tests. So the broadcast scan can have up to 20 to 30 dB of difference between the envelope and the minimum levels, the almost null positions. So 20 to 30 dB. With the traffic beam, it's not that bad. With the traffic beams, typically have a ripple of 2, 3, 4, 5, maximum 6 dB. So with the traffic beams, it would be possible with spatial sweeping and max hold to look for the maximum in the traffic beam. But if we want to use that approach to calculate from broadcast information to the traffic beam, then with the synchronization signal, it doesn't seem to be possible, because you don't know where you are, and worst case in the position you measure in the minima, in the null positions, and these are 20 to 30 dB lower than the maximum beam. And if you think of taking these low signals and putting it through this formula, then the measurement uncertainty, if you multiply this by 20, 30 dB, is vast. Yeah, so the measurement uncertainty is too high and not acceptable. Before we come to the end, I'd like to give you an outlook. That is the reason why we are just checking with the manufacturers which signal can be used and which signal has a clear ratio between broadcast power and traffic beam power. And currently we are discussing with Ericsson and Huawei to use for the input in that formula the so-called CRS, the cell specific reference signals. This is also a downlink reference signal and has a certain relationship to the other signals. And our current approach is to look into the cell specific reference signal, the CRS, opposed to the SSS and the PSS. So the primary synchronization signal and secondary synchronization signal, where we just have found out with latest simulations and latest calculations and also latest measurements that this signal is currently not good to use this for the calculation to the maximum exposure. Okay, so what we have learned from the session, what we take away from the session is all is pretty much still in flux in movements. It's a little bit still of looking with trial and errors and get an approximation to the ideal and final solution. That is also the reason why we will not expect, or we are not expecting, a finalization of the standardization before end of this year, and hence we cannot start before with the implementation, because we will definitely, Narda will definitely not do anything which is away from the standardization. Therefore, the market is too niche, and the risk of losing money into wrong approaches is too high. So we are not only following the discussions, but we contribute into these discussions, being member in the ITUT and being member in the ISC, and the rest of the standardization bodies. We are visiting and listening to them. So the way forward is pretty much clear, but still what is a little bit unclear is which part of the signal we will decode with the SRM 3600 to make sure that this is a signal which can really be used for the calculation to maximum exposure. Okay, with this final outlook, I like to end with the session.
Thanks everyone for attending today. Thanks very much, Volker, for your time. Very informative and interesting presentation. So thanks very much.
Yeah, thanks for your organization. Thanks for your contribution, Peter. Thanks to the audience.
Okay.
Have a great evening. Bye. See you next time.